if you see something quickly, you will see that the routers don't have any orange color link or light. Can we see that? I want to give a thumbs up if you can see that. Oh, okay. Before we require EMS, don't worry. As we proceed in the class, we get the require the 3 rules. So the first rule is you configure a network based on the network requirement. The second rule is that for configuring optimal networks, you must consider the 4 factors or the 4 criteria. Must consider QoS, availability, security, redundancy, right? Scalability, very important. So that's the second rule. The third rule is never cram anything in networking. That's my third. If you cram anything in networking, one, you forget. You will forget. If you cram out to subnet, you will forget. If you cram devices, you will forget. If you cram commands, you will forget. So don't even cram. When it comes to networking, don't cram. There's no point. Understand. Once you understand, you understand. Once you understand, you understand, right? Like, there's no other way to actually say it. Once you understand, you understand. Once you understand it, you cannot forget it. So that's the third rule. Never cram in networking. The fourth rule, we'll go to that maybe after the end of the class, right? So yeah, don't cram as much as possible. Don't cram. The reason why I'm able to teach these things because I understand. How do I understand? You can't say that you've not been understanding networking to a good extent since you've been in this classes, right? So understanding is a process. As you spend more time, as you interact with it more, you understand it. Right? One of the reasons why I understand some of these things a little bit better is slightly because in some ways I've had a level of physical experience, right? My first day in an organization's network, there was a switch problem. Like the first day I was entering an organization's network, there was a problem with the switches, and then we had to now troubleshoot VLANs, check the configurations, right? Right. And yeah, the work makes it easy as in a way, but it would only be easy when you actually put in the work. You can be in an organization's network and not understand shit. Right? You can have access to the firewall and not know what does what. Right? You can have access to the switch, check all the configurations, and not know what does what. So so you can still be lost even when you're in a physical space, right? You're in a physical network. You can still be lost, right? It's what the advantage of being a physical space is that it makes more sense when you see it physically, right? What you've learned now makes more sense because you are seeing it physically. But if you don't know it before you get there physically, it will still look like what's going on here? What are they talking about? Alima, am I saying what is right? Do you want to add to what I've just said? Why is Alima doing a thumbs thumbs up. Me that called your name. Is it your thumbs up I want to eat? Is your voice I want to hear? Not today, please. Okay. I said number 4, you will get that at the end of the class. Right. So not to overflog it, right? So you still need to like understand it like in your own room first, right? You still need to study hard as much as you can, right? It's when you study that it makes more sense when you see it physically. So let's say you miss number 2 and number 3. Don't worry, Aishat will type it. Aishat, you can type the 3 rules. Since you've been taking since you've been keeping tracks of the rules. So right. So where STP works is for example, you are in an organization and then you realize that for some reasons you are trying to access another VLAN and it is not going right. And then you as a network engineer, you are seeing a lot of packets leaving the switches over and over again. You are seeing network performance go down. And then you have checked the routers, and the routers are working fine, right? But for some reason, things are not just working fine at the access layer level. And that's why the OSI model comes into play, right? The OSI model helps you in troubleshooting because you start from layer 1. Why is this, for example, you're trying to reach a device on another VLAN and it is not going, right? That's the problem. And people in IT cannot reach people in production department. So you as the network engineer now, how do you pinpoint the exact problem, right? You first start from layer 1 of the OSI model. The layer 1 is the physical layer, and the physical layer is where you talk of cables and Wi-Fi, right? So you first need to ask yourself, oh, is the person's laptop in IT, is it connected to the access point? Is the Wi-Fi even, are we even going to connect, are you connected to the right network, right? That's the first question. If the person is connected, oh, fine. If it's not a wireless connection, you go to the person's physical laptop and check the cable. Oh, is this cable connected properly? You go to the switch. Is there a green light at the switch? So once that is checked, you know that okay, there's no problem with layer 1. So you go to layer 2. In layer 2 is where you have switches, right? The network interface card and all that. So you ask yourself, okay, as the switch learns the MAC address, is there a proper VLAN configuration on the switch? Is there a rule that allows those interfaces in that VLAN? Is the IT department in the proper VLAN? Right? Is there trunking enabled? Once you check that, okay, you ask yourself, okay, are there network loops? Once you are able to check all of that, right, at the layer 2, you go to layer 3. Oh, are we getting the proper route? Is the route table on the router accurate? is the firewall blocking the traffic, right? So you are troubleshooting. So the OSI model helps you troubleshoot, right? So there can be some, you can be in an environment, and then they are saying that, oh, there's an issue in the network, and then they are saying, oh, it's a firewall issue. You can't just say no, it's a firewall issue, or it's a router issue. You as a network engineer, you talk like a network engineer. You say, no, we need to troubleshoot. Come on. You can't just say it's a router. No. We need to troubleshoot. So, right, we troubleshoot, right? So you start from layer one. And then when you get to layer 4 and there's no problem, you get to layer 5, there's no problem, layer 6, there's no problem. You ask yourself, okay, is the DNS server working? I think DNS is a layer 7 protocol. If I'm correct. Yeah, it's a layer 7 protocol. So you ask yourself, are we resolving to the right, are we using the right DNS service, the domain that we're trying to reach, whether in the LAN or on the internet? Do we have the proper DNS configuration? For example, now if I show you my internet connection, you see that there's a DNS, and that's why I am able to reach certain. I'm using this DNS. This DNS is, I think, it's an MTN DNS, right? So that's how I'm able to, access the internet, right? So you ask yourself, okay, are we at the DNS level? Are we safe? If we are safe, you ask yourself, oh, are we even accessing the right domain name, right? Could it be that the website is down from the website's end? So that's how to troubleshoot, right? So one of the things you troubleshoot in the network is STP. Did we enjoy that? Did that make sense? This is 36 minutes. Wow. Did that make sense? Okay. All right. So that's how you solve problems as a network engineer. You think about it, and that's why you need to understand, right? That's why you don't need to cram. So if you cram, you would always be scared that, will I will I be able to solve it, right? But if you understand how a network works, right, you know that, oh, if I'm going to reach a domain name on the internet, if I'm going to reach an IP on the internet, you need a form of DNS. The DNS system has to convert that IP address to a domain name, right? So you need to connect to a DNS server. Talk about your mic, your camera is on, right? So that's how all these things come into play, right? So as a network engineer now, if you don't understand STP, you might not know that the problem with your network is STP, right? So that's why we're having this class, be able to break down what STP is. So, and like I said, STP is switch specific, and it's the protocol that ensures that there are no loops, there are no network loops, right? And who wants to explain what network loops are? Who wants to explain? You can just raise up your hand. This is an opportunity to enforce what you have learned. So who wants to explain? We need volunteers. Or I'm not going to be the one to explain it. So we need someone to, okay, Gabriel's hand is raised. I need 3 people actually. I need 3 people. In 2 minutes, 3 people that will just spend 2 minutes to just explain what network loops are. So Gabriel 1, who else? Me, I'm going to call somebody. Gabriel 1. Folakemi, network loop. LOOP. Network loop. Lube is a lubricant. Skincare people don't come. So Gabriel, Folakemi, will you be willing to help us out with that, with network loops? And then Aishat will also help us out. So Gabriel, let's hear you. Gabriel, you can unmute your mic.
Okay. Are you hearing me?
Yes, I can hear you.
Network is when packets are kind of in a network, when the packets are like colliding, maybe using a network diagram, let's say then all packets are colliding with themselves and still returning back to itself. So it's like it's moving a circular pattern or something like moving a circular pattern. So it's kind of bouncing out and still bouncing back to itself. So it's kind of going out and still coming back to itself. So it can cause a clash in the system. So that I understand maybe because of the routing table is not correct. So that's I understand it needs to be. I don't know if my explanation is kind of correct. But I think I can design one if I have a chance to.
Okay, that's cool. That's cool. Thank you for that. Folakemi.
Okay, so hello, can you hear me?
Yes, I can.
Okay, so for what I can interpret it, a loop like maybe the network is connected in a circle and keeps going round and round without stopping, and maybe makes the network slow or something.
Idea low matter. That's cool. Thank you for that. Thank you for that. Aishat, actually, like that's basically the summary of it. Right? Network is just looping around in circle or rectangles. Aishat.
Hello, can you hear me?
Yes, I can hear you.
Okay, so I think a network loop happens when there's so much traffic, right? When there's like so much traffic coming into a network and probably it doesn't know where, like, it doesn't know the right place to route the packets. Also, maybe it could actually happen in like layer 2 because maybe like when you're flooding so many like packets over the network and so a loop happens because it's just because like every like this the capacity of the packets that you're sending to a network is so it causes loop. I don't have the right words, but I hope that's correct, but that's what I can say about network loops.
Okay. Okay, cool. So, Alima, do you want to say anything?
Did you mention my name?
Yes, I did.
Oh, okay. Network loops, right? I think network loops are when switches in a network are connected to each other. I think more than 2 switches here in a network are connected to each other, and they keep flooding packets to one another on each of the interfaces, like in a loop. Is that the word for it? Yes. Basically, that's it.
Okay, you have added another angle to it. Daniel, do you want to add another angle? Daniel, are you there? Okay. So do you want to add to it? Hmm. Hmm. Nice. Thank you for that. So I think we've said it all. Right. Do I need to add anything to it? I think we all understand. You all understand. That's okay. Do I need to add anything else? I don't think I need to add anything. If you want me to add anything else, you can give me. They know the talks you look at. Okay. Um. Was there's nothing else to add after. But what I would just say is, um, especially at layer 2, right? Network, when you think of switches, I always tell us not to forget the F, FF, FFL, right? A layer 2 switch will either forward the packet, learn about the packet, or flood the packet, right? So let's go to our network topology. And you can see that we have a switch here, we have a switch here, we have another switch here, we have another switch here, another switch here, another switch here, and two other switches here, another switch here. And why are we having all these switches? It's because of the network requirement. The first network requirement is that we need to connect devices in Red Pea's organization LAN. And these are the devices in their LAN, right? They have laptops, printers, and so to create a LAN, we need switches, right? So you can say that this is a LAN, this is a LAN, right? This is also a LAN. This, excuse me, is a LAN. This is a LAN. This is also a LAN, right? So switches help you create a LAN. So this is why we have this with these switches, because we are creating LANs, local area networks where people can communicate. Now, why is this a LAN? This is a LAN. Why is this a separate LAN from this? It is a separate LAN from this because let's say we remove this connection, right? And we remove this other connection. The devices in this, the devices here will be able to communicate with each other. So exec will be able to communicate with CS, be able to communicate with HR and data department. They will all be able to communicate, right? Because they are all connected to the same switch. But exec won't be able to communicate with finance department, right? You won't be able to communicate with product department because it's on a separate switch. So you need some protocols to allow you achieve that communication. So this is a separate LAN from this. And even this LAN, we can still subdivide this LAN using VLANs, right? So we can ensure that exec stays in a VLAN, CS stays in a VLAN, and we can compartmentalize this LAN, we can break it down into VLANs to ensure that there's network segmentation. Right. So that's why we have these switches. Now, what are these distribution switches here? These distribution switches, right? There's something called a tier 3 network design. So a tier 3 network design breaks down a network into 3 layers: access layer, distribution layer, and core layer. So in the access layer, there are access switches. So these switches here that are connected directly to these devices are called access switches. The access devices, these laptops, they are all access devices. So that's the access layer. The distribution layer consists of distribution switches, right? So this distribution switch will distribute traffic coming from the access layer to other layers and to other devices. Let me give you a classic example. Let's say you want to communicate from this switch, you want to communicate from this department, right, to this department. What will you need? What will you need? Who has the answer to the question? What will you need to communicate from one LAN on a switch to another LAN on another switch? What will you need? Who has the answer? Who has the answer? No, that's not what I'm asking. Let me ask again. You are in finance department. You are a network engineer. I think this will be how we'll be going henceforth. I'll be asking very practical questions. Right? So you're a network engineer, and this is your network architecture. You have been required to ensure that there is 1 minute, please. I have a call. 1 minute. Okay, guys, I'm back. Something very don't let me even talk about it. Sorry. A friend called. Let's attempt to uh um yeah. So I might even have to maybe leave this call by 9:30. Uh, okay. So let's just quickly go back to what I was saying. I think I was talking about yeah. So the question is, you're a network engineer and you are supposed to ensure that there's connectivity between this this laptop in finance department, right? So this laptop in exec department. Now, this laptop in exec department is on this switch. This laptop is on this switch. So how would you ensure that they are able to reach each other? That's the question. What will you configure? What will you do? What are the processes you follow? So there's router on a stick using a router, right? And then there's layer 3 switch using SVIs. So there's the hybrid approach using both. Layer 3 switch with SVI is the preferred method. So that's the answer to that question. So answer is interval route. Oh, I said that the answer is interval routing, and there are two ways you can configure interval routing in a network. Either through router on a stick. So you create some interfaces on the router, right? So you do that encapsulation.1q command on the router, right? And then you turn the router to a device that can do interval routing. Or you use layer 3 switches to perform interval routing using SVIs, right? Switch virtual interfaces, right? And the more preferred method is using layer 3 switches, right? So in this network topology, you can see that we have this switch here. Now this switch here is performing a function. One is performing a distribution function. It is helping us distribute traffic from this switch to this other switch. So when we want to so our device for interval routing is this. Between this switch and this switch, we're using this switch for interval routing, right? So when this device wants to reach this device here, traffic will go to the switch. The switch will send it to this switch, right? So this switch will help us do the interval routing to forward the traffic to this switch. So this is called the distribution switch. This is in the distribution layer. Don't forget that. That is in the distribution layer. The core layer, all the devices here are the core, right? The RedPay core switch, the RedPay router, the ISPs, they are core to the organization because let's say all the devices in the network are trying to reach the internet. All the traffic will pass through these core switches. There's no negotiation. They must pass through these two core switches, right? So they are at the core of the network. So now, because a network must fulfill those four requirements of scalability, redundancy, right, QoS, and security, we have configured this network to have 2 distribution switches, right? So we have 2 distribution switches just to prevent a single point of failure. So let's say this switch goes down, maybe due to hardware failure or due to bandwidth, right? So you can see that this switch here is connected to this switch and this switch, right? And you can see that there's an orange link here and there's a green link here between this switch and this switch. See that this switch here is connected to this distribution switch and this distribution switch to get to this switch. So from this switch here to this switch here, we can follow this route, right, to get here. And we can follow this route to get here. So that's for redundancy. Now, this is where STP comes in. You can see this triangle. You can see this triangle. You can see this triangle here. This triangle here is a collision domain. Let's not go deeply into that. Just pick collision. Meaning that there can be collision in this network, in this connection you see here, there can be collisions, right? There can be network loops. That's why you see that there's an orange connection here. It's an orange connection here. Now, this orange connection you are seeing here is because of spanning tree protocol, right? And you would have asked yourself, why is the orange not here? Why is he here? Right? Why is this one not having any orange? You can even see that this one, everything is green. But on this switch here, they are green, and then this one is orange. Or this switch here, so everything is orange here. And this switch is, everything here is green here. And this switch is orange. Why is it that there's no orange here? Right? All those questions are answered by spanning tree. There's orange here, there's orange here. Why is there orange? What's going on? Right? No matter how you do it, it's going to be orange. Now let's do something quickly. This is how you know that switches learn. If I go into this switch and I shut down that interface, let me see. Tools, option, preferences, show port labels. So this interface is got this interface 1/0/2. So let's go into this switch. And let's go into interface. Enable configure terminal. Interface giga 1/0/0/2. Right? Let me confirm. Yeah. So shut down. So I've shut that interface down. Now let's see what's going to happen to this orange here. Right. After 30 seconds. Let's see what's going to happen. In 30 seconds, it should change to green. So let's just give it time. In 30 seconds, it will change. This is 9:10. It should change. See, it has changed to green. In 30 seconds, that's changed to green. Right. So there's something going on. Now let's enable let's enable it again. With the command no shutdown. and watch this same interface go back to green. This will go to green, so this one will become orange. But fast forward after 30 seconds, this is green and this is orange. So something is going on. Now, what is going on is what's going on is spanning tree protocol, right? So are we ready to investigate? Are we ready to investigate? If we are ready, give me a thumbs up. I'm ready to understand what's going on. Okay. I've not seen some people's hands. Okay. I'm just trying to just engage us. That's why I'm at like all bent on us talking or reacting. So let us investigate. So now that we have established that, but what we're doing first is even to isolate. So for now, we're isolating this triangle. Let us even just look at this triangle. And before we even look at the full switches, the connect this orange, this light blue boundary you see here represents like where all the switches are. Let me just remove these access points. I'll put them back later. All right. So this light blue represents where the switches are. So there's a network connection between all the switches. Yeah. But before we even look at the bigger picture, let's just look at this small picture here. Right. So this is a broadcast domain. This is a collision domain. There can be collision if there's no STP. Now, let's imagine that there is green here, and then there's green here. Do you know what's going to happen? What's going to happen is that so we are all assuming that there's, and I need someone to omit their mind so that person will represent everybody else in terms of feedback. Who wants to omit their mind? Gabriel, I don't want to hear your voice. It's not your voice I want to hear. Okay, so let's do Folakemi. Folakemi, can you unmute your mic so that we do this together? Okay, yeah, good. So, Folakemi, let's assume that this is green, right, and this is green. So, in traffic management, we know that red means stop, right? And in this, you can see that in this topology here, there's red here, meaning that no traffic can pass, nothing can happen except we do a no shutdown. All the interfaces are currently shut down, right? But if you go into the switch, the router, and we do configure T, and we do no shutdown, will this work? I don't think this will work. Okay, let's go into the interface. To go into the interface, options, preferences, show ports, and so this is gigabit 0.0.0.1.0.0.0. So if you do interface range, /0, 0/0/0/1, and we do no shutdown. That interfaces will be up, so we do exit. Right. interfaces will be up. So if you go into this router too, and we do enable configure T, and we do interface gigabit 0/2, and we do no shutdown, right? Both are now green, right? So let's go into this router too, and let's do enable configure terminal interface gig 0/2, don't shut down. Right, so they are all green now. So if I love not showing what's in the middle, it makes me monitor. So we can see that now we have green here. So green means traffic can go, right? Red, yellow, green. Red says stop, yellow says ready, and green says go. So you can see that in this triangle here, we have orange or yellow in quotes, saying that traffic cannot go through here. Any traffic trying to go through here must stop. It must follow this other lane, right? And then we're also saying that any traffic going through here cannot pass, right? Because there's a yellow signal here saying traffic cannot go. So if we're trying to get to this destination, from here. Let's say we're in finance and want to get to CS here. Once our traffic gets to this switch, it cannot pass through here. So it must pass through here to get to this point, right? So let's now assume that, Folake, you are there, right?
Yes, sir.
Yeah, so let's now assume that we have green here. Once the packet gets here, it can pass through here and here, right?
Yeah.
Yeah. So let's say the first traffic we send passes through here. It passes through here, right? Don't forget that a switch once does not length the MAC address of a device, it will flood that packet, right? So let's say that this switch has not length the MAC address of this destination that we're trying to reach. It does not know the MAC address. So if you go to this switch and we check the route table, I do some of these things so that we can remember some of these commands. Show MAC address. So this switch currently has only one MAC address length. So it does not length the MAC address of this device. So it will go to this switch, and this switch will do what? Will flood the packet. So the packet will go through here and it will go through here since it's a flood, right? Do we all agree? We all agree, right? So like you.
Yes.
So like are you there?
Yes, I can hear you.
Yeah. So do you agree with me that this to flood the packet?
Yeah.
So
Yeah.
yeah, and so yeah.
Yes.
Okay. Very good. All right. So that's what the switch will do, right? So when the switch forwards the packet here and forwards it here, don't forget that we're looking at this triangle. What will this switch do? It will also flood the packet because it does not know the MAC address. It will also flood, right? So when it floods, it will go here and it will go here. So this is where we're focusing, right? the packet from this switch will go here. And the packet from this switch that was flooded here and here will also go here. Now, when this switch gets the packet, it will flood to all other devices, and it will flood to this one too. Now, what's going to happen? This is where the loop will now start. Don't forget that this switch sent a packet to this, right? So this switch too will also flood to this, and this switch will flood that same packet to this. A switch will always flood packets to any device connected to it, except the device that sends that packet. So this one sends the packet, so it won't flood it back to this, it will flood to this. When this one gets that same packet, it will flood to this. So we'll be having floods. They will keep on passing it to each other. Did you all get that? Any questions concerning that? Is it clear so far? One minute, please. So there'll be a loop, right? So STP ensures that there are no loops. So it has put this interface in a state that will not forward packets. So now let us now consider the real scenario here. We have this blocked, no traffic can pass through this. So when we're trying to reach CS, right? When we're trying to reach CS, we will send traffic from the switch to this. Since here is blocked, we can't use here. So we'll go through here and we'll go through here. Even if this one floods, it floods to this, right? This can't send the traffic back to this because here is blocked. So we will not have a loop. This can't send traffic back to this because here is blocked. So we know that this is the only place we are going to use. Let's say this device wants to reach this legal device here. To still send the traffic to this because this device is connected to this device here. So it will still help us forward the traffic to this switch. So through this network, and let's say this one wants to even flood, there's already a connection here that blocks, so it can't get back to this. So we can't have a loop. Do you see how it works? We are seeing how blocking loops is very important, right? For like, are you seeing how it is important?
Yes, I am.
So there won't be any loop, there won't be any performance issue. We will not be having MAC address flapping. We will not be having the switch learn packets over and over and over and over again. No, we already have a blocking, we already have interfaces that are blocked. So what does STP do? The first thing, if you are making a note, the first thing that STP does is it prevents layer 2 loops by placing redundant interfaces in a blocking state. If you do not take anything from this class about STP, this is the first rule of STP. STP functions by placing redundant interfaces in a blocking state, thereby preventing layer 2 loops. So there's no advanced thing about STP that does not capture this. Now, don't forget I said redundant. So if it is not redundant, STP has no business. If it's not a redundant interface, STP has no business putting the interface in a blocking state. So if you don't have this connection at all, there's no point STP putting this interface in a blocking state. And just like I showed us, when I did a shutdown command here, right? This one automatically went to a forwarding state, right? Because there's no longer redundancy. So it is when there's a redundancy that STP comes in to help us manage that redundancy. So because on this switch now, there's redundancy. This switch can send traffic to this switch, can send traffic to this switch. So there's redundancy. So STP helps us manage that redundancy to ensure that though we are having a redundant network, STP ensures that we don't have problems with that redundant network. You know, redundancy helps us solve the problem of a single point of failure. But redundancy is creating another problem of a network loop. You see that networking is hard. we have solved a problem of having a single point of failure with redundancy. But we are creating another problem with the possibility of network loops, right? So STP helps us manage that problem that's been created by the redundancy, by the solution of redundancy. Does it make sense? If it makes sense, let's react with a thumbs up. If it does not make sense, you can give me a thumbs down. I know that some people will give me a thumbs down. Daniel. No, STP does not ensure. No, chill. No, chill. No, calm down. Before you explain, right? STP does not ensure that there's STP is not the one giving us the redundancy. But let me go to the network so I hear your points. So, what, Daniel, what's your point? Okay, so I think the problem is the choice of words, right? So someone wants to. Oh, okay.
Mine is a question.
Yeah, so I'm coming. I'm seeing
Okay.
Alima's comment, and that is it. And Ebenezer's comment too. Does STP not defeat the purpose of redundancy? No, it does not.
Do you know why I
is
asked?
that your question? Yeah.
Yes, I'm asking because like those orange lines make sure those packets don't go through like the switches, both switches at the same time.
Yeah.
And that means also traffic can go through them. So you're just
Yeah.
you're making sure to use one switch. And in that case, if we are depending on just one switch, does that not defeat like the purpose of redundancy? Or do we turn on the other switch maybe when there's a network failure and we now have to use the other? I don't know if you.
Exactly.
Oh, okay.
Exactly. Now, STP does not hinder redundancy. In fact, it ensures that redundancy works, right? Because redundancy is not, oh, redundancy is not, I have two cars and I am riding the two cars at the same time. You can't ride two cars at the same time, right? Redundancy ensures that if anything happens to my Benz, I can use my Lexus, right? So redundancy is to ensure that there is something to fall back on, not necessarily that we are using two things at the same time. Redundancy ensures that if there's ever a failure at any point, it will not affect us at all. Do you get? Yeah, that's the goal. It is not that, oh, we have two cars now, and so we must drive the two cars at all times. No, is that if fuel finishes in one, we can quickly revert, right, to another one. So that's what redundancy is to ensure that there is 100% availability. In case anything happens to one, we have another backup, immediate backup. There's no, we're now looking for how we go and buy a new switch. No, we have built our network with redundancy that if there's any failure, we will still be available. There will still be availability, right? So what you can do again with redundancy is to do a form of load balance, right? You can do a form of load balance, probably at the router level. Excuse me, probably at the router level, right? So at the router level, you can do a form of load balance to say that, oh, okay, send 50% of the traffic to ISP1, send 50% of the traffic to ISP2. Or we can say, oh, let's use SD1 policies. Send traffic that are going to youtube.com, Teams, any streaming platform, send that traffic to ISP2. Send traffic going to normal landing pages and normal basic websites, so ISP1, right? We have two ISPs that are redundant and we're using them at the same time through a load balancing mechanism. We could use ECMP, that's equal cost multi-path. That's a load balancing strategy. We can use least connection. We can use SD1 policies just to like configure that redundant devices that we have. Right? But at the switch level, STP helps us manage that redundancy to ensure that we don't have troubles with network loops. Right. So so is that clear? Is it clear to everyone? Yeah, Gabriel, you're very right. You're very right. Yeah. Aisha, thank you for liking my analogy. Yeah, so are we all clear on that so far? Are we all clear on that so far? If we're clear, we can give a thumbs up. If we're not clear, you can raise hands. Yeah, so I said the first rule of STP is it places redundant interfaces in a blocking state. Right? It ensures that it manages that redundancy. Right. So let me show us something else. You can see that on this switch, there are two redundant ports. So STP manages that redundancy, right? And so that in this switch, there are two redundant ports. So STP manages that redundancy. And there's orange here. Here, you can see that there are redundant ports. So STP manages that redundancy by placing a port in a blocking state. Now, there's a reason why this switch is all green, right? We will get there. So there's a reason why these two interfaces, even though they are redundant, are still active, right? We'll get there. We'll get there tomorrow. So let us build step by step. 1 minute, please. I need to respond to a message. Tasa. Sorry, I had to respond to a friend's message. Tomorrow is going. So that's the first thing about STP. So let's go to the second thing. In STP, there are 4 switch states or 4 STP states. There are 4 STP states. There's the blocking state, there's the listening state, there's the learning state, and there's the forwarding state. So there are 4 states in STP. They are called STP states: blocking, forwarding, learning, listening. I won't be able to go deep into all of that. To go deep into all of that, you pay premium price. That's just a joke, but for the sake of time and for the sake of complexity, I won't be able to go into all of that so that it does not become so complex and I lose all of us. But the 2 most important states are the blocking and the forwarding states. Forwarding means you are forwarding traffic. Blocking means the switch will not forward traffic at all. Right. So those are the 2 most important states: the forwarding state and the blocking state. So you will see that something happened when I ran this command. When I ran this interface gigabit 1/0/2 shutdown, you will see that it took almost 30 seconds. Let's count: 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 34 seconds, roughly 30 to 34 seconds for it to become green. Why? Because it was first in a blocking state, right? After it was in a blocking state, something happened to that interface. It came into a listening state. It came into a learning state, and then it came into a forwarding state. So in that 30 seconds, some things were happening for the switch to learn that, oh, this other port that I'm connected on has failed. So I need to quickly switch to the redundant port, right? So we saw that the redundancy is working because as one failed, the switch learned immediately to switch over to the other one, right? So the switch has to go through those states. It had to learn the topology again. Like the reason why this interface was able to switch to green was because this switch had to learn its topology to realize that, oh, do like say this interface that I'm connected to is not working. And don't forget that we didn't ping any device, we didn't do anything, and yet the switch was able to learn that this interface was down. How did the switch learn, right? I'm going to ask a question now, and we are supposed to get the answer, right? So, how was the switch able to learn that that interface was down? I want to see who's able to answer the question. Oh, said mad. I want to see who's able to answer the question. How did the switch know that that interface was down? I've mentioned it in passing in one of the classes before, but I want to see who is in the spirit. Yes, Alima is absolutely 100% correct. Using BPD. Absolutely correct. Absolutely correct. I'm proud. I'm proud of Alima. Oh my God, yes, yeah. Because I know I mentioned it. Like a switch sends BPDU frames out of its interface every what's in the PDF? Alima, can you unmute your mic? I should buy you Capriso. Alima, can you unmute your mic? Are you there, Alima? Can you unmute your mic? I want us to have a quick conversation. Alima, we can't hear you. I love how you are healing her. Yeah, your phone is hanging. Please. Okay, so Alima, did you cram that? Or did you
Hello? I could not unmute. My phone was hanging.
Oh, okay.
No.
did you cram it? For you to be able to answer, did you cram it? Or you understood it?
You know, cram it. I heard you. Like I remember you saying it one day that their BPDU are like packets that switches used to learn information about each other.
Yeah. And you understood why that was happening, right?
Yeah, I do.
Yeah. So once you understand it, it will always be in your head. It can never go. Right. Once you're able to understand it, right? If we go into simulation mode quickly, you will see that we're going to have packets. This orange packets, you can see these orange packets. They are BPDUs. If you see that all the switches are checking it, all the other devices are canceling it. If you investigate further, you will see that it's called STP BPD. It says the frame source MAC address was found in the MAC address of the multi-layer switch, blah, blah, blah. STP process receives a BPD on gigabit 10/1. BPD is a configuration BPDU. Receive BPDU, blah, blah, contains repeated information. So the BPDU is what switches use to learn about their network topology. And they always send BPDUs every 2 seconds. So if I play, you see that you keep seeing this orange stuff going out of the switch over and over again. They always send these BPDUs every 2 seconds. So see the time, 0.75, now 2.286. We're going to see the blue now, the pink, see, it has come out again. Right. So from this topology now, I can tell that this switch is the Baba, is the root bridge. Right, is the root bridge. You still understand what root bridge is. So let's leave this simulation. So every 2 seconds, a switch. What's going on in the chat? Oh God, people are making me laugh. Oh, fire on.
Sorry, that simulation you just did, I didn't get that.
Okay, so a simulation in Cisco Packet Tracer shows you how traffic is flowing through the network. So you can see that we've not pinged anything, this network, and we're seeing some packets flying left, right. These packets are called BPDUs, Bridge Protocol Data Units. A switch sends BPDUs out of its interface every 2 seconds. So every 2 seconds, time in seconds, every 2 seconds, a switch will always send BPDUs every 2 seconds. So you see that the next time it will send another BPD will be when it's on 4.4, roughly. These are just they're just broadcasts. So let's keep the time. Four seconds, right? Every 2 seconds. So on 4.4 or 4.2, they're about another and 4.4 again. And so that this is already out again. STP plug it again. So let's wait for one more time. So you see that's on 6.4 under seconds, it would send out another BPD. So every 2 seconds, that's how switches learn their marker, their network. So on like 6.4 again, you see another frame here. 6.4, we have seen another frame. So every 2 seconds in this network, this switch will always keep sending that BPD. And I can tell this topology that this switch is the root bridge. Now, for tomorrow's class, let me just write this down so that I don't forget. This switch is the root bridge, and we're going to see why it is the root bridge. So this is 9:51. We're going to stop here so we don't have information overload so that we can also rest. So before we end, I'm going to do a short 10-question quiz. Aishat, your hand is raised. Hey, you don't just do our quiz. Okay. You can speak.
Hi, okay, can you hear me?
Yes, I can.
Okay, thank you. I just want to ask, at some point in these classes that you're teaching us, are you going to give us any project, like maybe when you are done with
Of course.
switches, you can just...
Of course.
Okay.
So it is in the syllabus.
Is it like when we're done with networking as a topic, or when we're done with each topic, so that we can just learn as well? We can just practice as we are learning.
So my goal for now is for us to finish switching, right?
Okay.
So when we're done with switching, we'll do a project, not a project that we're going to document per se. It's an individual project for everyone. We'll do a simple project just to practice. I'll give us a question on switching and some scenario-based questions. We'll have a quiz in one of the classes. I'm going to set some scenario-based. Let me show us. I think I'm beginning to fall in love with Gemini. You're welcome. I'm going to fall in love with Gemini. Gemini created some interesting scenario-based questions for me. I'm preparing for an exam, and the questions this Gemini created for me, wow, I could not believe it. Why can't I find it again? Hey, God, yeah. When I opened it, and the questions were fantastic, right? So I'm just going to copy the same command, and I'm going to use it with STP. So we're going to do some basic STP questions. I think I'm in love with Gemini now. Let's do 10. Let's just do 5 because of time. Leave me, oh. Leave me, oh. I want it to be basic but tough. It should not be simple. All the best for you. Why are you giving me that? No, now we go do am now. I did not edit this one. Yeah. So let's this one they ask for root bridge. This is going to be too tough. I know we don't we've had a good time in this class. I don't want us to be sad. So I don't want to stress my brain this night. I need to conserve it for what I want to do tonight. A small business has 2 switches, switch A and B, connected by 2 separate Ethernet cables to provide redundancy. Without STP enabled, what is the most immediate and critical problem that will occur when a computer sends a broadcast frame? A, duplicate frames will cause the switches to continuously update their MAC address table, leading to MAC address flapping. B, switches will automatically prioritize one link over the other based on link speed. C, the frame will continuously loop between switch A and B, consuming all bandwidth, leading to a broadcast storm. D, the broadcast will be converted to a unicast frame, causing security filtering to fail. D is wrong, B is wrong. Now, inside between A and C, right? So what are we going for? It says the most immediate and critical problem. So who's going to answer this? You can unmute your mic and just answer. If you are confident enough, unmute your mic and answer. Okay. Oh, we've even answered on the chat box. Okay. Everybody chose C. All right, that should be correct. Wow, I'm proud of us all. Oh, nice. Which of the following STP port rows? Let's clap for ourselves. I need to clap. So everybody got it. Sharp. So okay, let's keep the streak. So the following STP port rows is specifically designed to block traffic for a segment, but listen to BPDUs to detect if the active part fails. You know, I just explained this now, right? So, which of the following STP port rows is specifically designed to block traffic for a segment, but still listen to BPDUs? Now, I've not taught us ports, right? So I think I have to answer this myself. Answer is alternate ports, right? You mentioned the blocking state. Yes, yes. In that last quiz, yeah, yeah. So this when this port was in that orange port, that orange state, it was an alternate port. I'll explain that tomorrow. I need to. So yeah, I've kept the streak for us. So let us continue. A network manager wants to ensure that the specific high capacity core switch is always the central point of the network's layer 2 topology. How is this preference configured using spanning tree protocols? I asked for basic. Why is Gemini asking tough questions? The answer is A. Yeah? Sorry. I didn't read the other options. Hey God. Yeah, it has to be the root bridge. Oh, why did I read the other options? The answer is B. I mentioned something about root bridge, right? So it's not, you use MAC address, right? You use the STP priority too. You must configure everything in such a way that that switch is the one that has the lowest STP priority. So it must be the root bridge, right? That's the answer. I didn't read the other options. My bad. My bad. A technician connects a user's computer to a standard switch access port running S802.1 DSTP. User complains that their network takes about 30 seconds to get an IP address and connect to the network. Now, we should be able to get this because we counted today, right? We should be able to get this. So what's the answer? Yep, that should be the answer. Answer is C. You know, it becomes sweet when you have been taught. It becomes sweet when you understand what's going on, right? That's the right answer. Hooray! Let me clap. Hooray! Hooray! You know, take solace in the fact that Mr. V might not even know the answer to that question. You know? Heaven is the goal. So you are doing well. You are doing well, you know. Asabi. Ebenezer, why is your hand raised?
I just wanted to ask you. You said
Yeah.
something about STP that and that, and it places redundancy in the port, right?
It places redundant ports in a blocking state.
Okay. Thank you.
Yeah. So let's see. Let's say this quiz won the suite. A network using PVST. Now PVST is a form of STP. Has two separate links between two switches. One link is 100 megabits per second copper connection, and the other is a 1 gigabyte fiber connection. Assuming default port costs, which link will STP choose to be the root port? This is a very simple question. And without even knowing this, as a network engineer, right, as a network engineer, just think from a place of network. You have a port that has 100 megabytes per second. That means you can download 100 megabytes per second through that port. And you have another port that you can download 1 gigabyte per second. Which of them will you want to use? Obviously, the 1 gigabit per second, right? So that's what this question is saying. That's the basic understanding. So A says neither link, both will be active and load balance traffic as they are on the same switch. B says the 100 megabyte copper link it has a higher default cost of 19, which is preferred by ST. C says 1 gigabyte fiber link, which has a lower default cost. D says the 1 gigabit link will be blocked. So what is our answer? What's our answer? From my explanation, what's the answer? Okay, okay. The answer is C. The answer is C. The lower the cost, the better. Yeah. So I'll explain this tomorrow. I'm happy that we are seeing some of this. Should we do 5 more or should we call it good night? Should we do 5 more or should we call it good night? Okay, 2 good nights. Should we call it good night or should we do 5 more? Yeah. Ebenezer, night. Okay, 3 good nights. Gabriel says 5 more. You can continue tomorrow, please. Good night. Okay. So I was to this class. So let's get feedback and 10-10 we're out of here. So we can make it 10 over 10. By 10, we're out of here. So we can make it 10 over 10. Wow. So it was awesome. It was insightful. Learn new things. You make networking enjoyable. Oh, but I said the remaining one is for good. That's fine. It does. Oh, at the blush. If you can see my face right now, my hair is messed up, but don't worry. So that it's like you can see my blushing face at the blush. Oh, oh. Yeah. So yeah. Thank you guys. So this is 10:09. My hair is very squeezed, right? And yeah. So we live by 10-10, so we can make it a 10 over 10. Chinasa, thank you to Alima. Thank you. It's not like to. It's Jen. It's Jen. Yeah, so it's 10-10. Good night, everyone. Have a 10-10 night. Bye.